In lecture 4, we have constructed a new theory of gravity, General Relativity, which satisfies the principle of equivalence that we studied in lecture 2, together with the principle of general covariance, and using the tools of differential geometry that we developed in the lecture 3. This theory is described essentially by the Einstein equations, and in lecture 5 we just found some of the simplest solutions of these equations. Now we have to test this theory, and testing this theory means, in this case, testing the predictions which are associated to these new solutions. These solutions lead to new predictions because these solutions describe the new form of the gravitational field, according to general relativity, around objects which are static and spherically symmetric. And these predictions have to do with the motion of test particles in those gravitational fields and the propagation of light in those gravitational fields. Then in this lecture, what we are going to do is precisely to study the motion of particles and the propagation of light in the gravitational fields that we constructed or derived in lecture 5. In particular, what we are going to do is to start with a generic static and spherically symmetric gravitational field and study the motion, the geodesic motion of massive particles, test particles, and the propagation of light in a static spherically symmetric background that we will not determine what the precise form. Okay, so it will be general. Then we will specialize those results for the particular case of the Schwarzschild metric, the external Schwarzschild metric. The internal doesn't make sense to study propagation because that's in the interior of a star or interior of a planet. And okay, we will see how the motion of these particles deviates from the expected motion in the Newtonian theory. These deviations will constitute the new predictions of general relativity, and finding those deviations will constitute an experimental test of general relativity. A bit later, these tests are usually the simplest ones are carried out in the solar system and have to do with the gravitational field of the sun or the earth. Then we are going to go a bit further, and because if you want to test that theory, it is very useful to compare the predictions of that theory with the predictions of alternative theories that will also could be candidates to theories of relativistic gravity. Okay, we haven't studied any of those theories, and probably we are not going to study it, but there is a formalism that is very useful to parametrize the different predictions of families of these theories. So you don't need to study these theories per se. The only thing that you need to study are the metrics that these theories predict for instance, static spherically symmetric fields, or or some other situations. And these metrics will be given in terms of few parameters which characterize the particular theories. You don't need to give the values to those parameters. You know that general relativity has some specific values for those parameters, but what you can do when you perform an experimental test is try to constrain the value of that parameter, find the value up to whatever errors. Okay, this means that you are not just testing the predictions of general relativity, but you are trying to exclude in this parameter space of theories, this space of theories that you have parameterized in this way, which theories are allowed by the experimental test, which of them satisfy the constraints on those parameters that you find through the experiments. This formalism is called the parametrized post-Newtonian formalism, And of course, it is based on the post-Newtonian expansion of general relativity. So first, we are going to review the post-Newtonian expansion or approximation of general relativity. This is something that we have done, but in a very schematic form in lecture 4, because we just studied the field produced by a particle and or how a particle reacts to the gravitational field in this approximation. Okay, and we saw that you recover the Newtonian result, which is a necessary thing. But there are corrections that we ignored, and we want to study those corrections in detail, because those are the ones that establish a difference between general relativity and the Newtonian theory. So first we will do this to study the post-Newtonian approximation to general relativity. So you will get essentially Newtonian gravity plus corrections. And then after that, we will study this parametrized post-Newtonian formalism. Okay, basically it will be more or less the same, but there will be parameters appearing in different places, multiplying the gravitational potentials. Okay, the post-Newtonian expansion is given in terms of several fields that we call gravitational potentials. One of them plays the role of the Newtonian potential in the Newtonian limit, but there are other potentials. I think we saw in lecture 4 that there were some potentials that look like or play the role of a gravimagnetic field. There are those, and there are a few more indeed. Okay, if you want to include all the possible or many possible alternatives to general relativity, and each of them will be essentially multiplied by a parameter or a combination of parameters that allow us to write this post-Newtonian approximation not just to one theory but to many theories. Once we have this parameterized post-Newtonian formalism, we will review, we will study the predictions of these theories, but not just for general relativity, but for all the theories which can be parametrized in this way. This will give us effects such as the precession of the perihelion of stars, planets, or whatever, in orbit around another planet or star or whatever. And this prediction will be given not just by a number, but by some function of the parameters. And if you compare with the experimental result, you can constrain the value of those parameters. So this is the value, or the nice thing about this parameterized post-Newtonian formalism. Okay, so just a couple of warnings. Since we are going to study the motion of particles and study how this motion differs from the Newtonian motion, you have to review what is the Newtonian motion of particles in a gravitational field. This is the Kepler problem. Okay, if you take a look at the lecture notes of this lecture 6, at the very end there are like 10 pages in which this classical Keplerian problem is reviewed. There is probably all of it. There are a few pages in which there are calculations associated to this so-called Laplace Runge length vector, because we are going to use this vector to characterize the precession of pericenters. So my advice is that you take a look to those 10 pages first, because I am not going to review them in the video. You are supposed to know all that. Okay, and this review is just, if you want, a courtesy, because we are going to use the same notation and so on. And the second warning is that in this lecture I am not going to do all the calculations, because as you can see in the lecture notes, some of them are really long, and well, in some cases there are conceptual steps or tricks that really need to be explained, and I will do so. But many of the calculations are just the standard calculations, okay, that you should be able to do. They are done in the explicitly, I think, in detail in the lecture notes, so you should be able to repeat them. But I don't think it makes sense to spend half an hour, expanding square roots or things like that in the video, because it would make them make the videos really, really long. Okay, so now we are ready to start. As I said, the first thing that we are going to study is the motion of particles in the external Schwarzschild geometry. But first we start with a generic static spherically symmetric field, because one of the things that we did in the previous lecture was to find the generic form of a static spherically symmetric metric, whether it is or not a solution of the Einstein equations in vacuum or some other kind of equation. So this is a useful starting point. Then we will specify the form of the metric. We will say that it is the Schwarzschild metric, and we will profit from all the results that we have obtained. Lecture 5, we proved that static spherically symmetric metric in 4 dimensions depends on just two functions of a coordinate that we called in a loose sense the radial coordinate. There are different ways of writing this most general metric. There are different coordinates that one can use, and here we are going to use this one, in which the functions that determine the metric are this lambda and mu, and the coordinate r is already by construction the coordinate which measures or gives you the area of the surfaces of constant r. So a surface of constant r and time has a surface 4 pi r squared. Okay, remember that this is the metric of the round to a sphere of unit radius and depends on the coordinates theta and phi in this way. So, well, if we are going to study geodesic motion, we have to write the geodesic equations, and the geodesic equations are given in terms of the Christoffel symbols. We can take the formula, okay, and just substitute the Christoffel symbols if we compute them, okay, or we can an alternative form would be to consider this functional and vary it, and then you find exactly the same equations, but maybe multiplied by something like this, because you get equations of motion that have a lower index. Okay, these two things are equivalent, clearly, but since I asked you in a previous video or a lecture, or maybe a tutorial, to compute these Christoffel symbols, then I am going to use these Christoffel symbols. I am going to write them just in a minute offline, so you don't waste much time watching the video. The only thing that I have to add before I do this is that the geodesic equation is not enough. You have to add to it the mass shell condition that tells you whether this particle is a massive particle or is a massless particle, okay, depending on whether this parameter alpha takes the values 0 or 1, because here, okay, the form of the equation is already telling you that the parameter with respect to which we take the derivatives is the proper time or the affine parameter. If it is something else, like the coordinate time or something else, okay, yeah, then we would have to write the equation in this way. Okay, but we don't know, in that case we wouldn't know exactly what this f is. So in this case, we are going to use simply the proper time or unaffine parameter, and then later we will see how we can work with the coordinate time, because it is sometimes what you want. The proper time is the time associated to the particle that is moving, so sometimes you want to see what this motion is like in the coordinate system in which you are, which is different from the one of the moving particle. Okay, these are the Christoffel symbols, the components of the Christoffel symbols, and we can start writing the explicit form of the geodesic equations. These are 4 equations, one for each coordinate. So I start with t. Okay, this would be t double dot plus gamma nu rho t x dot nu x dot rho equal to 0. Now I look at the components that have a t, and it is only this one. Okay, so it is RT. So, but I have RT and TR. Okay, of course, this is written in the most compact way. So I only write TR, the TR component, and not the RT because it is symmetric. But since there is TR and RT, I get a factor of 2. Okay, so really what I have here could be this. And now the value of this component of the Christoffel symbols is 1/2 lambda prime over lambda, which with the factor 2 give me this. Okay, it is understood that here the prime in in lambda and mu is a derivative with respect to r, because these are functions only of r. Okay, now you should take into account this. Okay, this is a double derivative with respect to tau, and this is a derivative with respect to r of lambda, and r dot is a derivative of r with respect to tau. T dot, this is clearly using the chain rule, just the derivative of lambda with respect to tau. Okay, so let me write it. This is T double dot plus 1 over lambda d tau T dot, but let me write this in this way. This is the tau dot d tau equal to 0, and we can also write it like this, taking this 1 over lambda as a common factor. See that this is tau d t dot d tau plus d lambda d tau t dot, and this is nothing but 1 over lambda d tau lambda t dot equal to 0. Okay, and this is the form of the equation that we are going to keep. So the t component is just t. Clearly this is a constant of motion, and this gives us an equation that can be integrated automatically, but okay, we will do that later, not immediately. Now the r component, again, is the same. Well, we just not the same, I mean we follow the same procedure or the same steps. Now I look at all the components of the Christoffel symbols that have an r, and now I have several. There is this one, and this one. The 3 of them are diagonal. It says that they have TT, RR, and zeta zeta. Okay, so let me take this out, and there are no factors of 2 or anything here. So I have 1/2 lambda prime mu, and this is t dot square plus now is this a minus 1/2 mu prime mu r dot squared, and finally minus r mu theta dot squared equal to 0. Okay, sorry, I'm afraid I forgot this one. Sorry. So there is one more. Okay. So there is plus sine square theta phi dot square equal to 0. Okay, this is the not phi dot because this is sine theta, the value of this, so there is a minus. Okay, really I have to write it in this way, phi dot squared equal to 0. Next, let's consider the theta component. We have to look for the components of the Christoffel symbols that have an upper theta. So index, which would be this one and this one. Okay, so I write everything in one shot. This one, the first one, is off diagonal, so it has, you have to take a factor of 2. So it's 2 over r dot theta dot minus sine theta cosine theta phi dot square. Okay, this part of the equation can be written like this. If I take out a factor of 1 over r squared, I have the theta dot, r squared, the theta dot d tau plus 2r dot theta dot minus this stays the same. And now observe that this is just d tau of r squared. Okay, sorry, this is r squared. So the whole thing is, okay, and this is the definite form, the final form of the equation that we are going to use. D tau r squared theta dot minus sine theta cosine theta phi dot squared. Okay. Finally, we have the phi component. Well, why should I write phi dot? So it's phi double dot, and now we look at components. Well, we search for components of the Christoffel symbols with an upper phi index, and there is this one and this one, and both are off diagonal, so we have to multiply by 2, and we have plus 2 over r dot phi dot plus 2 times cosine theta over sine theta dot phi dot equal to 0. Now this is the same structure that we found here, the first two terms, so we know that we can rewrite these two terms in this form. Phi dot, so this is the derivative of r squared phi dot, but it is not so difficult to see that here we have something similar. This is the derivative of the sine theta with respect to theta, so really this is the derivative with respect to tau of sine squared theta and phi dot. So in the end, you combine all these things, and this is 1 over r squared sine squared theta d tau r squared sine squared theta phi dot equal to 0. In the case of the theta component, we didn't, well, the equation here is not, well, it's just has a more compact form, but it is not an immediate integral or anything. But here you have this equation is a statement of conservation of this quantity, okay, and you can integrate it immediately. So we have these 4 equations, and we also have this mass shell condition, okay, which is nothing but lambda, which is GTT times T dot square minus 1 over mu, minus 1 over mu is drr, so this is r dot square minus theta, sorry, r squared, which is a common factor of theta dot square plus sine squared phi dot square equal to 0. Oops, sorry, to alpha, which could be 0 or 1, as we said before. These are the 5 equations that determine or dictate the motion of massive particles and the propagation of light in a static, spherically symmetric gravitational field. Now we want to simplify this set of equations as much as possible, and we start by integrating those which can be immediately integrated, like the T component of the geodesic equation. That gives us that lambda T dot is a constant that we call epsilon, and whose meaning we will discuss later. And the other equation that can be integrated immediately is the Phi component of the geodesic equation. That gives sine r squared sine squared theta phi dot equal to some other constant that we call L. Okay, we can use these 2 integration constants, epsilon and L, to eliminate T dot and phi dot from the rest of the equations. Before we do that, let's discuss something else. This is something that we have already mentioned before. These 5 equations are not independent. We can derive a linear combination of the geodesic equations from the mass shell condition. Remember that if we have this mass shell condition, okay, for whatever value of alpha, if I now take the derivative with respect to tau of this condition, I get an equation which is of the form 2g mu nu x dot mu, and then the geodesic equation now written with the free index nu. Okay, this means that we can use, instead of one of these 4 equations, or a combination of them, we can replace it by the mass shell condition. Which one should we eliminate, or should we not consider anymore? Well, the most complicated is the r component of the geodesic equation, this one. So we are going to use the T component, the theta component, the phi component, and the mass shell condition that I am going to write now. So the T component just gives T dot is epsilon divided by lambda. The r component we are going to eliminate from this problem, because we are going to use the mass shell condition. Then we have the theta component, and let me write it in this way. We have the tau of r squared theta dot, and I multiply everything by r squared. So I have minus r squared sine theta cos phi dot squared. Clearly, if I multiply, I could replace this phi dot squared by L. If I have 1 more power or 2 more powers of r, so this becomes r squared, and I need sine cube theta, so I have sine 4 theta, and then all this can be replaced by L squared. Okay, so I delete everything and I replace this by cosine phi L squared equals 0, and typically we write this with r squared sine squared theta. This is the second equation. The third equation, well, this doesn't look nice. The third equation is just phi dot equal to L divided by r squared sine squared theta. And the last equation that we are going to use is the mass shell condition, but with T dot replaced by epsilon divided by lambda. And okay, theta dot stays as it is. Sorry, there is a theta missing here. And okay, maybe we split this equation like this. If I have phi dot square, well, clearly this is L squared divided by r squared sine squared theta equal to 0, and here I have epsilon divided by lambda. Okay, epsilon squared, as a matter of fact. Okay, and these are the 4 equations that we have to study. Okay, one thing that one typically does is that one fixes theta equal to pi over 2. This is the same as saying that all the motion takes place in the equatorial plane. Okay, but in order to do this, I mean, why is this possible? Well, clearly it is it solves certain equations. If I set theta equal to pi over 2, then theta dot is 0, and then the first component of this equation is 0, and in this, sorry, this instead of phi should be theta. Okay, so cosine of pi over 2, this means that something is wrong. Okay. So the whole equation is satisfied. And then in other places, this term will disappear, and this sine square theta becomes 1. Here, things are simplified by, but the question is this a particular solution, or is this the most general solution in some sense? Because if this is just a particular solution, okay, it's okay, but then the resultant equations cannot be used to study all the possible situations and all the possible solutions. Then we have to justify why we can do this, okay? If this is general, or we are missing something by doing, by setting theta equal to pi over 2. So let me first eliminate these lines, just to leave the equations clean. Okay, and let's see. Well, we have found two integrals, immediate integrals, or two constants of motion, epsilon and L, and there must be a justification for their existence. These are constants of motion of the particle or the light ray moving in this background. And when we studied constants of motion of particles or light rays moving in a gravitational field, we associated them to the existence of Killing vectors. Okay, so for each Killing vector, there is a constant of motion. Okay, so this makes you expect that there are at least 2 Killing vectors here. In fact, by construction, we know that there are 4. There is a Killing vector, okay, which is just the derivative with respect to time, because we have chosen the coordinate adapted to the time-like Killing vector to construct this metric, so to write this metric. So we know that this by construction there is this Killing vector. The metric is time independent, so this is what you expect. And there are another three vectors that whose expression I gave you in spherical coordinates, and they look like this. Cosine theta, sine theta, d phi, then k2 is cosine phi d phi minus cosine theta sine theta d phi, and k3 is just d phi. The first of these Killing vectors, this one, generates infinitesimal time translations, and the quantity, the conserved quantity associated to it, will be the energy of the particle. The other three generate rotations with a fixed axis, an axis in a Cartesian coordinate system which is associated to the spherical coordinate system that we are using. So for instance, K1 generates rotations with axis x1, so they are rotations in the x2, x3 plane. Together, these three generate all the rotations in space, all the spatial rotations, and this is the SO3 group. One way of seeing this is to write the Killing vectors in the Cartesian coordinate system that I mentioned before. Okay, this representation will be useful for us later. Now, just as we said that the energy would be the constant of motion associated to K, that let's call it K0 just to distinguish it from the rest, the quantities, the conserved quantities associated to K1, K2, K3 will be the components of the standard angular momentum, which are the spatial components of the relativistic energy momentum tensor. Now let's see this association in more detail. Remember that the quantity associated to the vector k, the conserved quantity, is given by, and now I am including all the factors, by this expression for a massive particle. So for the vector k0 that generates time translations, what we have is the following. Okay, now k0 mu is only different from 0 for mu equal to t, the time component. This means that this is only, and in fact it is 1, so we have gt, and nu can only be t because the metric is diagonal, the kind of metrics that we are considering, and here this is t dot. But gtt in the coordinate system that we are using is the function that we have called lambda of r. Okay, so let me call this constant of motion E divided by c. Okay, I know it is the zeroth component of the form momentum. So, and if I write this in the form lambda t dot equal to minus E divided by mc squared, this is the constant that we found before and we called epsilon. So epsilon is minus the energy of the particle in units of mc squared. Okay, epsilon is just an adimensional parameter. This gives us the interpretation of epsilon, and this justifies the existence of this conserved quantity. Now we have all these three quantities, p, k, I, that we are going to call Li divided by c. These are the three components of the angular momentum, and they are given by this expression again. Okay, this is a complicated expression if we want to compute it for all the k's. Well, what we want to do now is, okay, first notice that these are three conserved quantities and we have found only one. So you may wonder if there is really another one, another two in our system. well, that is not the case. The point is that these Li's are not completely independent, or not all of them are really meaningful. Let's see first one property. Okay, if you compute Li xi, please don't do it in spherical coordinates, do it in Cartesian coordinates. This is minus mc xi, and now I use this representation. This is epsilon I j k xj, and then the component k comes here, and well, the metric has no mixed time space component, so this has to be another spatial component. Let me call it xl. It doesn't really matter. The only thing that we want to show here is that this is clearly 0 because this is symmetric in I and j, and epsilon ijk is antisymmetric, so this is 0. What does it mean? Well, this equation means that if Li are the components of, well, this should be divided by c according to my definition. If Li are the components of the angular momentum vector, the standard spatial components, then the motion, because this is not always the most general value of the coordinate xi, but this is referred to the components xi of the world line of a particle. The motion of the particle is contained in a plane which is orthogonal to Li. Okay, so if I have this vector L, I know that the motion will take place in this plane. Now, it is convenient to choose this plane in the best possible way, so to simplify our equation, just as we choose the origin of coordinates or anything else. We can choose freely the origin of coordinates when the space is invariant under translations. Then any point is as good as any other point. You choose the one which is more convenient for you. The same happens with this plane. Because there is invariance under rotation, you can choose this plane with the orientation which is best for you. That orientation would be in the x1, x2 plane, so orthogonal to the third component of L3. In other words, we want L3 or L to have this form. Okay, so the motion takes place in the plane orthogonal to L3. You can now see that okay, let's study what is L1 and L2, and at least for one of them, and you see that this is equivalent to set theta equal to pi over 2. Okay, when you set theta equal to pi over 2, L1 is equal to L2 and is equal to 0, and only the component L3 is different from 0. This is done explicitly in the lecture notes, so I'm not going to do it. You do this directly in spherical coordinates, because this is where this condition is most easily applied. Okay, and the only thing that I'm going to do is to write L3 divided by c, the one which is not 0, and it makes sense to compute it. Okay, K3 mu is only dd phi. Okay, so only the component mu equal to phi is different from 0 and takes the value 1. So this is minus mc g phi, but then mu has to be phi because the metric is diagonal, and this is phi dot. And g phi is r squared sine squared theta. And this is the quantity that we called this part. Yeah, this is what we called L. Okay, so this conserved quantity L is L3 minus L3 measured in units of energy. Okay, and this is the meaning of the conserved quantity L, or the constant of motion L, is the only non-vanishing component of the angular momentum. You could have another two, but they would not be really meaningful. It just means that you can start with this solution in which you set theta equal to pi over 2, and you can rotate it, okay? And you generate another two numbers which are associated to the two angles that you use to rotate this solution. But you don't gain anything new. You just rewrite everything in a general way. It is not necessary. This is just the meaning of these integration constants. Okay, so the moment that you set theta equal to pi over 2, then your equations simplify even more. You eliminate one of them and you eliminate certain terms in the equations, and we are left with this equation, the equation for t, the equation for phi. So now sine squared theta is 1, and the mass shell condition, which takes the form epsilon squared divided by lambda minus r dot squared divided by mu minus L squared divided by R squared equal to alpha. And to this we have to add, if you want to reconstruct the solution in 4 dimensions, theta equal to pi over 2. And this is the set of equations that we will study. The last one doesn't do anything. Now, how do we solve this system of equations? Well, we can almost immediately solve this differential equation because it only involves r of tau and derivatives of r of tau. You can use this to solve for r of tau if you know how to integrate this equation. Okay, this is a function of r of tau. This is another function of r of tau. So if you know lambda and mu, and you are good enough to know how to solve these differential equations, or you use some numerical procedure, you find r of tau. Then you come here and you can integrate this equation as well. Okay, how would you do it? Well, you have d phi over tau. Okay, and you multiply everything because we are physicists, we can do this. Okay, and you integrate these two sides, and you also come here, okay, and you do exactly the same. You get epsilon divided by lambda of r of tau d tau, and this will give you the phi of tau, t of tau, and finally you have theta of tau equal to pi over 2. So this is a complete solution. So now we are going to focus our efforts in solving this equation, which is the most complicated. And first, notice that you can rewrite it in this form. Plus V alpha of R equals 0, where V alpha is whatever you have here. Okay, so written in this way is 1/2 of alpha plus L squared divided by R squared times mu, which is a function of R, minus epsilon squared divided by 2 mu divided by lambda. This is a trivial thing. To rewrite it like this, you just take r dot squared and whatever else you have, you call it a V of alpha. And you see that this is effectively the equation of a point particle, okay, which moves in some coordinate that they call r, a classic Newtonian particle, okay? It's a reinterpretation of the same equation. It's the same equation that you would have if you had a Newtonian particle moving in the direction r only, subject to this potential V of r. And this is the equation that tells you that the total energy of the particle is 0, the kinetic energy and plus the potential energy is 0, and the potential energy is given by this expression that depends on this integration constant L squared, on this other integration constant, and this value alpha, which depends on whether you consider massive or massless particles in your original problem. So this is an analog problem, but it is very useful to consider it because we know, I think you have studied already in the institute how to solve this kind, at least qualitatively, to understand the motion of particles in a potential. Okay, if you know that the total energy is like this, you just study the potential, you find the minima, and then you know qualitatively how the particle moves. And then this motion in this particle, this effective motion, we can translate into the real motion in this four-dimensional space-time. This is what we are going to do. In the massless case, alpha equal to 0, you know that tau is not really the proper time, it's just the affine parameter. So we are free to rescale it, and we are going to rescale it by the constant L. Oh, let me rewrite these equations in terms of the new parameter. Okay, so this would be B0 of R, and the idea is that I am going to divide everything by L squared. Okay, so this V of R is what I get from B with alpha equal to 0 by dividing by L squared, and this L squared I reabsorbed into tau here. Okay, so it doesn't change. It is this. It's a new tau, but it doesn't really matter. And now V0 after I divide by L squared becomes half. Now L squared divided by L squared, you get nothing. So it's mu minus epsilon divided by L squared, sorry, over 2 mu divided by lambda. So what we learn from this is that the motion of light only depends on the quotient epsilon divided by L, or if you want L divided by epsilon, which we call B from now on. So what is the meaning of this B? Let me rewrite this in terms of B. So this would be 1 over R squared mu minus 1 over 2 B squared mu divided by lambda. So in order to see what is the meaning of this new parameter B, I want to rewrite this equation instead of an equation of tau, R as a function of tau, of R as a function of phi. Okay, so we can change the variables in this way. Oh, we have dr d tau is dr with respect to phi, and then d phi with respect to tau. Okay, and this is r dot, and this is phi dot. So dr d phi is just r dot divided by phi dot. Okay, remember that when we rescale this by tau by L, here there is a factor upstairs and a factor downstairs, exactly the same. So this expression will not change, but phi dot in this new rescale tau will be given by 1 over R squared only. So let me just compute the r d phi squared. Okay, according to this result, this is just r dot divided by phi dot squared. So I have r4 from this phi dot, and then I have r dot squared, which is minus 2 v0 of r in this case. So it's minus 2 r4, and then we have v0, which we have computed here. Okay, I can take as a common factor 1 over 2 and mu as well. And I am going to take also r squared, I think. Well, no. So this is 1 over r squared minus 1 over b squared lambda. The factors of 2 cancel, and this is r to the fourth 1 over b squared lambda minus 1 over r squared. Okay, what happens when whatever the motion of this light ray is, suppose that it's a motion which is not bound, okay, to the whatever gravitational object we are studying. So it's not an orbit, a closed orbit or anything like that. It's not. It is a motion that comes from infinity and goes to r going to infinity again. So we want to study what happens when r goes to infinity. When r goes to infinity, lambda goes to 1, and certainly 1 over r squared goes to 0. The dominant term here is this one, okay, because this one would go like r squared only, so the dominant term is the one with this r squared, sorry, r fourth divided by b squared. Okay, so at long distance, you can solve this equation, okay, in this asymptotically, and what you find is that you take the square root, so this goes like r squared divided by b squared, the phi divided by b squared, and this gives you minus 1 over r, and this like b divided by b squared. So ignoring the sign and everything, this is just something very qualitative to give you one interpretation of b, which, by the way, when I take the square root, I should have taken also the square root here. This goes like b, and this is what allows us to interpret b, because, okay, here it is the center of coordinates, okay, and this light ray goes into some direction. This is r, okay, this is our coordinate axis, phi. And the point is that this tells you that the product r phi, which is this, okay, this is b, is constant. So when this goes very far away, okay, so this means that the motion when you are very, very far away is a motion parallel to this line here. Okay, so b remains constant, and the interpretation of this parameter b then is that is the impact parameter. So the conclusion is that instead of two independent integration constants as you have in the massive case, in the massless case, the motion is determined by a single constant of motion which has the interpretation of the impact parameter.